frequency signal analyzer based on NV center in diamond. And basically we are going to present an radio frequency signal analyzer. And my group members are Akhilesh, Suraj and Vishnu sir. I am just giving a brief and basic overview of this, and then Akhilesh will present the experimental part and Suraj will explain the results and Vishnu sir will conclude all this. The basic outline of our presentations are motivation, the basic motivation behind our presentation, why we are going to make this IR analyzer, NV center basic idea, then quantum diamond signal analyzer का basic concept, experimental setup, and then key results, limitations and outlook. The basic need behind this is that the traditional analyzers are limited by analog to digital converter and we need the broadband. These are highly power consuming and bulky in nature. Then we need to modify them, and as we work on this, it completely consumes all the microwave spectra by changing its magnetic field and diamond separation, which will explain by Akhilesh. And our main aim is it will work on room temperature, it's compact in size and low power spectral analyzer using NV center. NV centers are nitrogen vacancy. It is a type of point defect in diamond where we substitute nitrogen in place of carbon, and a vacancy is also present in the adjacent position of nitrogen, and this combined will form the NV center. It's in spin triplet state, and corresponding to this S is equals to 1, S is equals to 1, we can divide these states as MS is equals to 0 and plus minus 1. The ground state is triplet, and this metastable state is in singlet form, and when the magnetic field is 0, the separation between them is 0 field splitting, which is equals to 2.87 gigahertz. When we apply a 532 nanometer laser, before applying the laser, the atoms are in thermal equilibrium and are in ground state. When we apply the laser, these atoms will start exciting to the excited state. This photoluminescence process will emit a red light. And when the magnetic field is not equals to 0, then splitting will start occurring in the energy levels, and these will start to split into these. Applying an external static magnetic field to the NV center leads to Zeeman shift, and which is observed here. When we increase the magnetic field, the separation between them increases with frequency. Now I would like to invite Akhilesh for further.
Afternoon, everyone. So, as Jyoti discussed, the basic idea behind the NV centers. So we develop a quantum diamond signal analyzer. Basically, it is recognize the radio frequency. It is the idea behind this concept is making that to analyze the radio frequency and microwave with the use of NV centers in diamonds. So ensemble of NV centers in diamonds, and we apply a magnetic field gradient, and magnetic gradient maps microwave frequency to spatial positions, and photoluminescence image with a camera, and a local PL drop indicates signal frequency. As we applied the magnetic field, of the different spatial position in diamonds. So it creates the different frequency at the different NV centers in diamond. Um, so as we apply the microwave inside the NV centers, so peaks. So where the frequency matched with the NV centers frequency, resonance frequency. Uh, some pixel data reconstruct radio frequency spectrum in real time. And next, this is the experimental setup we get. So we use the diamond dimension of 4.5 to as you can see CVD sample and NV and magnet neodymium sphere which has a 1.3 centimeter diameter and tunable magnetic field which provide the 1 Tesla magnetic field, and by changing the magnet diamond distance they can tune the NV centers spin transition frequencies. The transition from, so we have a frequencies from 0 to -1 state to 10 megahertz to 21 megahertz, and from 0 to +1 we get so we assign that 2.87 gigahertz to 27. And so when we apply a laser light, green laser light of 532 nanometer continuous wave laser in diamonds, so it absorbed by the NV centers and so it is absorbed by the NV centers and gets to excited state, and at the time of de-excitation so we get a fluorescence light of 630 to 637 approx to 800 nanometer light. And after that when we apply the microwave, then it creates the it flip the ground state wave it flip the ground state population to 0 and ±1, and applying the laser it flips continuously to decay via high excited state to intermediate state called metastable state, and then we finally get 0. And finally we get microwave drive via 1 nanometer loop anti-linear diamond. In this figure we can see that we use a laser light on the diamond crystal. So this is a laser light falls on the laser, and then next the filter polarizer and microscope objective. The use of the filter polarizers to get the it allows the pass only fluorescence light, and this part is the blue and red part is showing the magnetic for use the magnetic field gradient. Basically this is the two part. One part is applied for the NV magnetic field across the axis through the NV centers, and second one is applied for the gradient, magnetic field gradient. So, and there are 3 NV centers, and the circular part is showing the microwave antenna. And the next calibration and processing. So NV center absorb green light and then emit red photoluminescence. This photoluminescence depends on the NV spin state, which allows optical detection of magnetic resonance. And the emitted which is photoluminescence is stored in 110 lattice, and each pixel linked to nitrogen vacancy resonance frequency via ODMR scan. ODMR scan just is when light de-excites from the excited state to intermediate level and via ground state. So we observe the intensity is decreased. and mask M identify the resonant pixels and the spectrum via this equation, and SNR signal to noise ratio depends on NV density and collection of efficiency. So, this is the key results and ray and bandwidth. So, I will present. So, next the key results is basically we get the tunable range of 10 megahertz to 27 gigahertz, and our goal is to get the 25 gigahertz, and the lower limit set by the ground state level anti-crossing, and which can be shown here. So, this is the frequency versus distance between the magnet and the distance and energy centers. As we increase the distance, so frequency we can show the variation this frequency, and this one is the frequency, the pixel versus a frequency graph. Actually, when we get the image from the camera, so every pixel is assigned to a particular frequency, which is mapping a particular frequency on the on each pixel, and the last one is the frequency versus as a pixel, the same reverse. So, next सूरज present करेगा.
This is the frequency resolution for intrinsic line width. It is 500 kilohertz, and for the best measurement, for the best measured of full width half maxima, it is this is lower line width, which is 1 megahertz at lower frequency, and higher field increases line width 50 megahertz. This graph shows microwave power versus resolution, and amplitude dynamic range. This is ODMR contrast. As we increase microwave power, ODMR contrast will increase, and there is a sharp dip. For the detectable range, 23 decibel to minus 17 decibel, and dynamical range is 40 decibel. This is frequency versus contrast. As contrast increases, the dip is more sharp. And for the temporal resolution, this is using for real-time image enables millisecond scale temporal resolution. Means if for 1.8 gigahertz frequency, we can resolution power is 22 millisecond. For 9 gigahertz frequency, it is 20 millisecond, and for 23 gigahertz frequency, it is 600 millisecond. And for higher frequency, low contrast and long integration.
So I think at the last I'll try to conclude what they have talked about. So the QDISA, the quantum diamond spectrum analyzer. So generally the conventional, if you look at the conventional analyzer, it's FFT based, and that thus sampling rate is not that high. So with this, what they have showed that okay, they can increase the sampling rate, they can increase the they can go to the lower higher resolutions, and that's where they also have the compact system, because it's at room temperature, it's just nano diamond. Another main advantage is it's a low power analyzer, because if you look at other FFT analyzer or other ion trapped crystal analyzer that has the cryogenics and it takes several watt power. So with this NV centers, these analyzers can be used for different applications, especially for the radar monitoring or any kind of magnetic sensor applications. And now the range, if you look at the range, it shows in that paper it shows 25 gigahertz, but it can go beyond that. So people are also trying to use the multi frequency microwave signals. So in that case, they can go up to many fold of this gigahertz range. Bandwidth, if you look at, it's a 4 gigahertz, and the resolution, so that is up typically 1 megahertz. It's limited again by the camera. So another factor of concern here is the improvement. So one thing is optical collection. So how much photoluminescence photons we are trying to collect with the CMOS camera. Then there is a design. If there is a misalignment of the magnet to the NV center axis, then there will be some error, and the how much density, the NV density, the nanodiamonds had. So applications, as it can be used for any kind of electromagnetic communication monitoring. That's all. Thank you. Yeah, yeah. Yeah,
There's two questions. Why do they use a magnetic beader in this demo? You think
magnetic beader.
this bowl,
Oh, this.
no, below,
Oh, is a spherical.
this spherical.
Okay, so that they have the homogeneous magnetic field. No, no. This the spherical magnets they have used. That is especially. That's.
So they can, when they get close enough, they can generate, somehow uniform magnetic field, but very strong gradient.
Yes, very strong gradient. Yes.
So it's a very strong gradient along
To the axis, yeah.
along this
Axis, yes, yes.
So they my colleague, they tried really different kinds of
Okay,
systems,
okay.
and actually the simplest,
Yeah,
that was the simplest,
yeah.
and that was actually amazing how we can get a peak of about 1 Tesla
Oh, yes.
with this kind of thing, which is, and it's even, if you have 2 bits, you put them, they go
Collect,
and they explode. It's not so easy to manipulate actually,
Yes, yes.
because it's so, the magnetic field is so strong that we had one that went, and it was like a little bit of bullet.
But I think with the sphere, they can, if they just have to have the higher magnetic gradient, they can use some kind of tapered magnets where they have like with the aligned and I think very strong interactions.
You're right. The magnetic field is rather homogeneous at the
Yes.
strongest condition, but somehow other techniques, because otherwise the alignment, so it has to be very well aligned
Yes.
on the axis of the NV. And so they use a diamond which is 110.
Zero, yes.
Why they have done that choice?
Because that's the magnetic axis of the NV, the diamond. So.
Yes, but they could have taken 111 or 100, like all the experiments I showed in the lectures. But they choose the specific orientation 110. Do you have an idea why?
In that case, we have to NV center along the axis of this magnetic field.
You have no.
No,
It's
no.
only
This is
one.
one
There is
NV
only
center.
one, but it has great advantage. It has a strong advantage. First, it's in plane,
Oh yeah.
so it can
It's a
really be like that.
yeah parallel to the plane.
And then
perpendicular to the.
So somehow you, as I remember, you have two dipoles, and the two dipoles, are in the plane perpendicular to. It's like two incoherent dipoles in the plane perpendicular to the
This axis.
PNV here. Okay, so basically you will have one dipole. Suppose you have linear. Let's take it like that.
Yeah. This you are saying, okay,
So
this.
you look, they detect light. You have a light detection from that.
Yeah.
So this is optimized for what kind of dipole that emits light?
It's a parallel.
What?
Uh,
Just you would like it, for this detection, the dipole here, how should be oriented? Like that or like that?
like plane parallel to the plane. Yeah.
Okay. So now look, I have that, and here I have two dipoles, and they are incoherent. So basically, it's whatever you can excite them. And basically, if you have a kind of this, an a polarization like that, you will excite one in-plane dipole, and let's say the other one is like that. And this one, it's exactly the one that emits the best light.
Okay.
So somehow it's a kind of compromise to optimize both the NV detection and the detection of the luminescence from the NV, and at the same time an easy way where you can really have the gradient in this configuration. Whereas for the other system, you always have at 37 degrees, so it's always a little bit complicated. So that's why this, because at the end you sacrifice, there will be only one. And why there won't be, why we don't care about the other families of NV? It's related to the previous talk.
That is the one is perpendicular to that axis will
be.
be.
We align the B field along the axis of one NV family. And why do we don't care about? Why we do not care about the other? No. Look, you should remind what was said in the previous talk. They should know the answer. The question is, here, in all the paper, they consider only one NV family. While the three other orientation, that would be, for instance, this is one, there will be distributed like that. Why we do not care then? We do not care about them.
Computation is direction dependent, like the axis.
Okay. Go ahead.
Because of the planar symmetry of the.
If the NV center axis are aligned with the magnetic field, I won't couple it with it effectively. So
Yes. So somehow for the other one, as they are off axis, they will see an off axis magnetic field very strong, because this is, let's say, 1 Tesla. So they will see a huge magnetic field, but now off their axis. And as you said in the previous paper, as you shown in the previous paper, that completely mix the state, and you do not have any more the sensitivity to the magnetic field. So you do not have any OGMR. And it's even better because somehow you quench the luminescence. So the luminescence is really decreased for the other families of the NV center. So somehow this enhances the contrast of the good family, the OGMR contrast of the good family.
Yes.
So the strong magnetic field applied that has two features. And somehow it kills, let's say, put it like that, the contribution from the other families, the off-axis contribution. Off-axis for the other NV. Good?
Good. But this is C-axis or A-axis?
This is what? Sorry?
It's a C-axis or A-axis? If you look at
What matters is the axis of the NV.
Okay.
And the axis of the NV are somehow, of course, set by the
The
diamond axis.
Okay.
Which, and basically,
That's
110,
axis,
it's a good, or it's something quite, that is well suited for many applications.
Thank you. Yeah. Done?